Hello, we're going to start a problem involving simple harmonic motion and a mass spring system, but this is what I call like a two-step problem. It involves solving for something in between before we can solve for our final goal. Okay, so I took the liberty of highlighting a few steps and writing some stuff down in preparation for this, so the video isn't that long. But you notice that I highlighted some important information in the problem itself. Now, this is something that you can do to help you understand the problem, the given conditions that you'll need to solve for what you're looking for. Okay? So the fact that it's a frictionless surface is already important because that tells us that the motion isn't damped, that it is definitely simple harmonic motion, that if there's no friction on it, no damping on it, it would continue on forever, that the mechanical energy is conserved and whatnot. Okay, so that actually is important. The block is pulled away from unstrained position, the equilibrium position, to 5 centimeters or 0.05 meters and released from rest. This tells us two things, that essentially this is our amplitude. And the fact that it's released from rest we'll need later on to solve for the phase constant. But we'll get to that later. The next piece of information that we will need, very important, is that the period of this mass spring system is 0.64 seconds. So I put that down here, and we'll actually need that to solve for something else later. And then get to the goal. Okay? Now, we'll need to break this down a little bit. It says here that show that when, keyword when, the speed of the block is equal to 0.3 meters per second, the distance is 0.041 meters from equilibrium or the unstrained position. Okay, so I wrote this down, hopefully it's not that confusing. It's asking for the position when that is the speed. Okay, so the unmentioned secondary goal is time. Okay, so we'll have to solve for time in between before we get to the answer. Oops. Okay, and which formulas will we need? So we'll need this formula for angular frequency and these two kinematic formulas from simple harmonic motion itself. There's also acceleration, but we will not need that one. Okay, so let's go ahead and get into it. The first thing I'm going to do is actually solve for the phase constant, and we do that by looking at the initial conditions. Okay, and it's actually not too bad. It just says that at t equals 0, it's at rest. V sub 0 is also 0 meters per second. Okay, now I'm going to use this velocity equation, which is very conveniently right here. So at v of 0 times 0, I'm going to use that to solve for phase constant. Okay, anything times 0 is 0, and we're told that it's at rest. So if I divide both sides by negative omega a, it doesn't matter what that is, it's going to result in zero as well. As a matter of fact, it's just 0 by itself, no units. Okay, and I'm going to move all the way over here, bring this all the way onto the other side. So I get that sine of phi equals 0. Okay, that's a ratio. So how do I solve for phase constant itself? Take inverse sine, run out of room, and I get just phi by itself, sine of 0. So what is the smallest value, or within 2 pi, that the sine of that angle is 0? Well, in this case, it's going to be 0 radians. Okay, so that is well and good. We'll save that. Okay, and so now we're going to use another kind of boundary condition. And we're going to solve for the time when the speed is 0.30 meters per second. Okay. Now, once again, I'm going to use the velocity equation for simple harmonic motion. But now I don't need this phi part, because that is now 0. Okay, and so solving for time, and omega is, I'm going to use a different color as well, is 2 pi over t sine of, once again, pi over capital T, the period, t. Gotta love color. Okay, I'm actually going to keep that as our VF. And if I solve for t, I'll have to do a couple of things. I'll have to cross multiply here. We're actually going to get a minus tvf 2 pi t, and then we're going to have to do inverse sine that entire thing, and that gives us still minus but now notice there's no more sine on the other side, the right side. Okay, I'm going to cross multiply again. So whatever is here on the top goes on the bottom, and vice versa. And I get this expression. Okay, and I am intentionally going to leave this in its algebra form. It may look a little bit complicated, but trust me, this will beautifully work out in the end. Okay, and we are going to keep it like this. Okay, you can solve for it, but then you'll have to learn how to keep the answer in your calculator using a memory store or using the answer button, which most calculators have nowadays. But I would encourage you to keep it like that. Okay, so now we get to the nitty-gritty, the actual thing that you wanted to solve. Okay, so going back to the position function, which is very straight up, just cosine. Once again, this is now 0 radians, so I don't need to write that at all. But just doing that for the sake of, and this x of t is going to be this big T right there. I don't have enough room to put it, so I'm going to use dot dot dot. Okay, so I'm going to use a lot of brackets now. So we're going to use, this is still 2 pi over t, while our time, let me use black. Wow. Okay, and you can see that those two things cancel out. Okay, so that's how you know that you're kind of on the right track when things kind of work itself out and kind of the solution becomes more elegant. Okay, so now all I have to do is actually plug in the values based on my given here at the beginning, right here. So it's like plug and chug. Oops. That's in meters. You don't have to write the units, but I require my students to do that, so I will go ahead and keep that in there. The period. Speed. And something missing here on the bottom. Okay, so forgot to write, there is an A, and all of that. There you go. So that would definitely make your answer wrong if you did not include that. And how would that, how do I know that? Is because the units here cancel out, seconds, okay? But whenever you apply something in a sine, or any trig function for that matter, it should actually be a unitless ratio. So I have meters here, so it should cancel out there, and definitely it becomes unitless. So there you go, that all should work out. And one thing I want you to see here, cosine. Cosine of any value will be from -1 to 1, whether in degrees or radians. So I know that the answer that I should get somehow should be, whoops, less than that number. Now I already know the answer is 0.41, but if you plug that in, and you can pause if you want and plug all of this in your calculator, make sure you know you keep whatever's on the top is on the top, bottom is on the bottom. You can do it separately. The answer that you'll get should definitely be 41 centimeters, which definitely is indeed less than 0.050 meters or 5 centimeters. Okay, so feel free to pause, look back, and see any parts of the procedure that you want. Hope you all enjoyed. Ciao.